When dealing with a 400 amp service for a quadplex, several options exist for distributing power to the 4 units in the mechanical room. Each option has different cost and convenience implications. Firstly, consider a square D 400 amp meter main with a Polaris tap. Install the square D 400 amp meter main. Come off the two 200 amp breakers into a can. Then use a Polaris tap to connect the main feed to the 4 units in the mechanical room. This approach offers a clean and convenient solution. Secondly, explore a 400 amp meter main with a custom tap. Locate a 400 amp meter main with 10 spaces. If finding one readily available proves difficult, consider fabricating a custom tap block to distribute power to the 4 units in the mechanical room. Thirdly, consider a 400 amp meter base with taps. Install a 400 amp meter base. Then install separate 200 amp disconnect switches or circuit breakers below the meter base. Subsequently, use tap blocks to connect the main feed to the 4 units in the mechanical room. Fourthly, a 400 amp socket meter main with taps could be used. Install a 400 amp socket meter main with either 3 or 4 sockets. Then, use tap blocks to connect the main feed to the 4 units in the mechanical room. Evaluating these options requires understanding cost considerations. The square D 400 amp meter main with Polaris tap, while clean and convenient, is typically more expensive. A custom tap option necessitates custom fabrication, potentially increasing both time and cost. The 400 amp meter base with separate disconnects or breakers is generally less expensive than the square D option, but it introduces additional components. The 400 amp socket meter main with taps is also less expensive, but it relies on a socket meter main, which may not be the preferred choice for all installations. Considering convenience factors, the square D meter main simplifies installation. Custom fabrication requires precise engineering and potentially longer lead times. Separate disconnects or breakers introduce more points of failure and require more wiring. A socket meter main might be less familiar to electricians, possibly increasing installation time. When selecting the best option, consider a balance between cost and convenience. The square D 400 amp meter main with Polaris tap offers a good compromise. It ensures a clean and reliable installation with minimal additional labor. However, if budget constraints are significant, exploring the other options might be necessary. Electrical codes and local regulations always take precedence. Consult the National Electrical Code or NEC and local amendments for specific requirements related to service sizing, overcurrent protection, and wiring methods. Ensure that all components are listed and labeled for their intended use. Verify that the chosen solution complies with utility company requirements for metering and service connections. Proper grounding and bonding are crucial for safety. Install a grounding electrode system in accordance with NEC Article 250. Bond all metallic enclosures and equipment to the grounding system. Use appropriately sized grounding and bonding conductors. Overcurrent protection is essential to protect equipment and wiring. Size circuit breakers and fuses according to the ampacity of the conductors they protect. Ensure that the service disconnect is readily accessible and properly labeled. Wiring methods must comply with NEC Chapter 3. Use appropriately sized conductors for the intended load. Protect conductors from physical damage. Secure and support conductors in accordance with code requirements. Load calculations determine the required service size. Calculate the total connected load for each unit in the mechanical room. Apply appropriate demand factors as permitted by the NEC. Ensure that the service has sufficient capacity to handle the calculated load. Short circuit current rating SCCR is an important consideration for all electrical equipment. Verify that the SCCR of all components is adequate for the available fault current at the service location. Install overcurrent protective devices with sufficient interrupting rating. Coordination of overcurrent protective devices ensures selective tripping. Perform a coordination study to minimize power outages. Select circuit breakers and fuses with appropriate time current characteristics. Proper labeling and documentation are essential for safety and maintenance. Label all circuit breakers and disconnects with their intended function. Provide a complete set of electrical drawings and documentation. Maintain accurate records of all electrical work performed. Qualified personnel are necessary for all electrical work. Only licensed electricians should perform electrical installations and repairs. Ensure that all personnel are properly trained and equipped. Regular maintenance can prevent problems and extend the life of electrical equipment. Inspect and test electrical equipment periodically. Repair or replace any damaged or worn components. Keep electrical equipment clean and free from debris. Safety precautions are paramount when working with electricity. Always de-energize circuits before working on them. Use appropriate personal protective equipment (PPE), such as gloves and eye protection. Follow lockout/tagout procedures to prevent accidental energization. Ground fault circuit interrupters GFCI protect against electric shock. Install GFCI protection in areas where water is present, such as bathrooms and kitchens. Test GFCI receptacles regularly to ensure proper operation. Arc fault circuit interrupters are SI protect against electrical fires. Install SI protection in bedrooms and other living areas. Test of SI circuit breakers regularly to ensure proper operation. Surge protection protects against voltage spikes. Install surge protective devices (SPD) at the service entrance and at sensitive electronic equipment. Select SPD with appropriate surge current capacity. Power quality can affect the performance of electrical equipment. Monitor voltage and current levels. Correct any power quality problems such as voltage sags or harmonics. Energy efficiency can save money and reduce environmental impact. Use energy-efficient lighting and appliances. Install occupancy sensors and timers. Consider renewable energy sources such as solar panels. Consider future expansion when designing an electrical system. Provide adequate spare capacity in panels and conduits. Plan for future loads, such as electric vehicle charging. Cost-benefit analysis helps in choosing the most appropriate solution. Compare the costs and benefits of different options. Consider the long-term cost of maintenance and operation. Life cycle assessment evaluates the environmental impact of different options. Consider the environmental impact of materials and manufacturing processes. Choose sustainable materials and practices. Risk assessment identifies potential hazards and mitigates risks. Identify potential electrical hazards. Implement safety measures to mitigate risks. Emergency planning prepares for power outages and other emergencies. Develop an emergency plan. Install backup power systems such as generators or uninterruptible power supplies (UPS). Train personnel on emergency procedures. Continuous improvement is essential for maintaining a safe and efficient electrical system. Regularly review and update electrical procedures. Seek feedback from personnel and customers. Implement changes based on feedback and experience. The NEC Article 220 provides guidance on load calculations for dwelling units. Use the standard calculation method or the optional calculation method. Consider the general lighting load, appliance load, and heating and cooling load. NEC Article 230 covers service entrances. Ensure that the service entrance conductors are properly sized and protected. Install a service disconnect that is readily accessible. NEC Article 250 addresses grounding and bonding. Install a grounding electrode system that is effective. Bond all metallic enclosures and equipment to the grounding system. NEC Article 310 provides ampacity tables for conductors. Select conductors with adequate ampacity for the intended load. Consider the ambient temperature and derating factors. NEC Article 408 covers panel boards. Install panel boards that are properly rated for the available fault current. Ensure that panel boards are readily accessible and properly labeled. NEC Article 547 addresses agricultural buildings. Use wiring methods and equipment that are suitable for the environment. Protect electrical equipment from corrosion and moisture. Understanding the specific requirements of the installation is crucial. Consider the location of the building, the type of occupancy, and the intended use of the electrical system. Consult with a qualified electrical engineer or contractor to ensure that the installation meets all applicable codes and regulations. Proper planning and execution can result in a safe, reliable, and efficient electrical system for the Quadplex. Remember to prioritize safety and to comply with all applicable codes and regulations. Furthermore, future-proof the electrical system for evolving energy needs. The growing adoption of electric vehicles and the increasing demand for electricity in homes necessitate forward-thinking electrical planning. Therefore, incorporating future-proof elements in the electrical system design is a prudent decision. One important aspect of future-proofing is to provide adequate spare capacity in the electrical panel and service entrance. This spare capacity will allow for the addition of new circuits and equipment without requiring a major overhaul of the electrical system. For instance, consider installing a larger electrical panel than currently needed, or running larger service entrance conductors to accommodate future load increases. Another key consideration is the installation of conduit pathways for future wiring. Running empty conduits to strategic locations throughout the building will facilitate the installation of new wiring without the need to tear into walls or ceilings. These conduits can be used to add circuits for electric vehicle charging, solar panels, or other future electrical needs. Electric vehicle charging is a rapidly growing trend that will likely impact the electrical demand of residential buildings. When designing the electrical system for the Quadplex, it is wise to anticipate the potential need for electric vehicle charging stations. This can be achieved by installing dedicated circuits and conduit pathways for future charging stations. It is also important to consider the capacity of the service entrance and paddleboard to ensure that they can accommodate the additional load of electric vehicle charging. Solar panels are another technology that is becoming increasingly popular in residential buildings. Installing solar panels can significantly reduce the building's reliance on grid electricity and can even generate excess electricity that can be sold back to the utility company. When planning for solar panels, it is important to consider the location and orientation of the building to maximize solar energy production. It is also necessary to install the appropriate wiring and equipment to connect the solar panels to the electrical system. Energy storage systems, such as batteries, are becoming increasingly affordable and can be used to store excess solar energy or to provide backup power during outages. When planning for energy storage, it is important to consider the size and type of battery system that is appropriate for the building's needs. It is also necessary to install the appropriate wiring and equipment to connect the battery system to the electrical system. Smart home technology is becoming increasingly prevalent in residential buildings. Smart home devices can automate various functions such as lighting, heating, and security, and can also provide valuable energy savings. When planning for smart home technology, it is important to ensure that the electrical system can support the power and communication requirements of these devices. This may require installing additional circuits or upgrading the network infrastructure. Building automation systems can optimize the energy performance of the building by automatically adjusting lighting, heating, and cooling based on occupancy and other factors. These systems can also provide valuable data on energy consumption, which can be used to identify areas for improvement. When planning for building automation systems, it is important to consider the complexity of the system and the level of control that is desired. Renewable energy credits (REC) are tradable commodities that represent the environmental benefits of generating electricity from renewable sources. By purchasing REC, building owners can offset their carbon footprint and support the development of renewable energy projects. Demand response programs incentivize building owners to reduce their electricity consumption during peak demand periods. By participating in demand response programs, building owners can earn financial rewards and help to reduce the strain on the electrical grid. Green building certifications, such as LEED and Energy Star, recognize buildings that are designed and operated in an environmentally sustainable manner. Obtaining a green building certification can enhance the building's reputation and attract tenants who are committed to sustainability. By incorporating future-proof elements into the electrical system design, building owners can ensure that their buildings are ready for the energy challenges and opportunities of the future. This will not only reduce the building's environmental impact, but will also enhance its value and competitiveness. When implementing any of these options, always prioritize safety, adhering strictly to the National Electrical Code and local regulations, and consulting with qualified electrical professionals to ensure a reliable and compliant installation. Remember that electrical work can be dangerous, and only qualified personnel should perform such tasks.